Now, we will look to that nature of the surface force. For that, let us consider a small fluid element in the shape of a tetrahedron. In the shape of a tetrahedron, such that 3 of its faces lies on the 3 coordinates plane. Okay. A tetrahedron, that is a figure with 4 faces, but this tetrahedron is such that it has 3 faces lying on the 3 coordinate planes, and the 4th face is an inclined face. Let us take it this way. And these 3 mutual orthogonal direction, let us take them to be A, B, C. That is, the unit vector along this direction is A, unit vector along this direction is B, and the unit vector along this direction is C. And the tetrahedron, so this makes one face lying on this coordinate plane, AC coordinate plane, this face lies on coordinate plane BC, and this third face lies on the coordinate plane AB, this face, and the inclined face now this becomes now let us say what is the force acting on this element, the surface forces that are acting on this element. We did not, or rather for sake of simplicity, we will not write that x and t thus, because you are thinking of a small element, and in our discussion that the position is remaining unchanged and the time is also not changing. So, that position vector and time in that expression we will not write, we will simply write t as function of n. Yes. Let us say these elements are area are delta A1 is the area to which A is normal, that is the face that is lying in the BC plane has area delta A1. Similarly, the face which is lying on AC has area delta A2, and this third face which is lying on this plane AB has area delta A3, and the area of the inclined faces inclined face is let us say delta A. Area of the faces are like this. Inclined face with normal n, this normal we are denoting let us say n. Delta A1 face with normal actually it is minus A. we are taking only the normal which is pointing out of the volume. So, the normal is actually minus A. Similarly, delta A2 and delta A3, delta A2 corresponds to minus B and delta A3 . So, what is the total surface force acting on this element? Total surface force acting on this element. Okay. Then yes. Now, can we express this delta A1, delta A2, delta A3 in terms of delta A? You see this delta A1, delta A2, delta A3 are the projection of the area delta A in three coordinate planes. So, what is the relationship? How can we write delta A1? What is delta A1 as an example? What is the projection of n along A? You know the unit vector, say what it is. So, what is delta A1 then? Total n dot A into delta A. And in our notation we can write this as n j A j delta A and others also. Similarly, delta A2, delta A3. Then if we write it in the earlier equation using the vector notation, this T which is force per unit area is a vector. So, the T will denote as by T I. Okay. So, using that subscript notation, that vector T will be written as T I. sorry, the first term there is delta A. Or we can take only one Now, let us consider the equilibrium of this fluid element. Consider the equilibrium of this fluid element. This is the surface force acting on this element. In addition, the volume force is also acting on this element. Okay. If we consider again that the volume force acting on that element is again that rho f delta v. So, total volume force and this is the force that is being applied on that triangular element. So, if there is any change in acceleration or if there is an acceleration, then that acceleration will also depend on delta v. This is equal to the rate of change of momentum, is not it? Mass into acceleration. This plus this is mass into acceleration. And mass into acceleration equal to total body force plus total surface force. This left hand side is proportional to delta v, the first term on the right hand side is proportional to delta v, the second term on the right hand side is proportional to delta A. Okay. Now, think of that this element is being made smaller and smaller in such a way that its shape and orientation is remain same. Okay. In such a situation, you can see that the left hand side term and the first term on the right hand side will approach to 0 at a much faster rate than the second term. Agreed, because the first term, there is left hand side term and the body force term and this acceleration term or the inertia force term is proportional to delta v, which is cube of the characteristic size, while this total surface force is proportional to square of the characteristic size. Now, if you are making the element smaller and smaller is what? That is the characteristic size is becoming smaller. So, obviously, this will decrease at cubic order, while this will decrease at second order. So, the decrease in these two are much faster than the decrease in the last one, surface force term. However, this condition if this fluid is at rest, if it is equilibrium, this condition will valid always. So, even in the sense when this characteristic size or this volume approaches to 0, at that limit also this equation holds, or this element is in equilibrium. How is it possible? Two terms are decreasing in as a delta x cube, say, or delta L cube, while another is decreasing as delta L square. How can they balance? That is possible if this is entirely 0. This is possible only if this total surface force is entirely 0. Otherwise, this will not be balanced by these two, because these are much smaller than this. It cannot balance. Only possibility is that this has to be 0, only then it can be balanced. Followed this argument? So, this gives us that now see this vector n and vector t, that is the surface force per unit area and the normal to the surface, is independent of your choice of axis system. Whatever axis you choose, the normal will remain normal and the surface force will remain the surface force. It is irrespective of or independent of axis system. So, the left hand side is independent of axis system. Consequently, the right hand side also has to be then axis independent. Or you see this, the left hand side is a vector, the left hand side is a vector, and on the right hand side n j itself is a vector. So, this is something product of some quantity into a vector with a vector, and the result is still a vector. Look to the right hand side, this is product of two quantity, one is this bracketed term, entire bracketed term, and this n j. N j is a vector, this we are not sure what it is at this stage. It is because it gives a j t I, these are some sort of product of two vector, a is a vector, t is also a vector. So, a j t I is a product of two vector, but it does not look like your scalar product, does not look like your vector product, that is dot product and cross product. The notation is entirely different. The dot product is a j t j, but it is not a j t j. So, it is not dot product. So, this is not scalar, this is neither a vector, because a cross product of a vector gives a vector, cross product of a vector gives a vector, this is not cross product. It can be a vector, but we have seen that cross product of a vector will be denoted by that.
But it still can be a vector.
Let us see how can it be vector, say if a j and t I. looking to a say those standard matrix notation for tensor, the scalar is called a zeroth order tensor, it is singly one element. Vector is basically a first order tensor with having one column. Vectors are usually represented by a column matrix. Vectors are usually represented by a column matrix. Now, if you look to in that sense A j and T I, can you think of this product? Now, anyway, whatever this quantity is, this is what we are getting, but this must be independent of the axis system, because the left hand side is independent of the axis system, independent of the choice of axis system. Whatever axis system we choose is independent of that axis system, because the normal remains normal and the surface force remains the surface force, whatever axis we choose. Also, you see that what it gives, this gives the ith component of the force, the end result of this right hand side, all these products will be finally the ith component of the force, that is what it is equated to left hand side. However, we see that this product itself depends on the normal to, but this normal is in the direction of this normal again, which is of course not the direction of this force. This normal A j is in the same direction as this normal N j, both are j, both will have the same value, no. Whatever j we choose, for I equal to 1, see this will be, there will be a sum of it, this j is repeated within this. So, for simplicity, let us say if you want to write what is T 1, the first component of the force, let us write it T 1, and this n all the time we are not writing, okay. Just we are can you write? Someone can tell me what it is? I you have fixed 1. A 1 T 1 A, here we are writing, because otherwise you might think all of them are T 1 and then let us cancel it, okay, because they are different. B 1 T 1 B, C 1 T 1 C into n 1 plus a 2 T 1 a plus B 2 T 2 b plus B 3 T 3 c into A 2 B 2 C 2, last one is C 2, C 2 T 1 C, B 2 T 1 C, yes, all are T 1. A 2 T 1 a, B 2 T 1 b, C 2 T 1 c into N 2 plus the third term A 3 So, that will be the first component of this surface force on this surface. Anyway, this the term in the bracket is called the stress tensor. This is what the stress tensor, and of course, denoted by 2 subscript, and now we will write that simply as what notations did I use? Use the same notation. Say T T I j T I equal to, this we will write as a small t, T I j in j. This T I j is called the stress tensor, which is a second order tensor, and as you have seen here that irrespective of the choice of the axis system, independent of the choice of axis system, like the vector, normal vector and force vector, this stress tensor is also independent of choice of axis system. And this T I j, which you can look to this, you can understand what is the meaning of this T I j. T I j is the, of course, force per unit area in the direction I on a plane to which j is normal. T I j is force per unit area. We are not mentioning that at position x at time t, that is always there. These are all function of position and time, as you have mentioned in the beginning. T I j is force per unit area in the direction I acting on a surface which has the normal in j direction. Okay, here the first subscript I refers to the direction of this force, and the second subscript j refers to the direction of normal to the plane on which it is acting. And again remember that in the right hand side, which is now written as product of 2 quantity, one tensor and one vector, one second order tensor and one first order tensor, it is summed over the index j, the index that represents the plane. So, in general this stress will have 9 elements. Along 3 direction, and in each direction again 3 component because of 3 direction of the normal. However, we will now see that as such this is not so, that all these 9 components are not independent. And this we can now again see using the rotational equilibrium. Using the translational equilibrium, we have found that the surface force is basically have the stress nature, the nature of the surface force, and further if we consider the angular or rotational equilibrium, we can see that all the components are not different. For that, you can consider an element of any shape. You can consider an element of any shape and think about a point, a fixed point within that volume, and then take moment of all the forces that are acting and equate it to the angular rotational inertia force, moment of inertia into angular acceleration. Now, consider rotational equilibrium. Again, let us start with consider an element we are just fixing up a point within the control volume, just to take a moment about that point. Let us say that this is that point, fixed point call O, and some element like this. At any position, surface forces are acting given by that T I j n j. So, what is the moment of the surface forces? The surface force is the surface force acting at any point which position vector is say x is T I j n j, which is function of x and t. We are not writing that all the time explicitly. So, T I j n j into of course delta A, which T I j n j is force per unit area. So, the force is T I j n j delta A. So, what will be the moment due to this force? Cross product of that force with the distance from the point O. Write it using this index notation. The distance you can write r, so it is r cross f. You can start from there, r cross f, and r cross f will be denoted by epsilon I j k r j f k. Okay. Now, that f k will come from that T I j n j. So, f k you have to write in such a way the result is, so T I j n j you have to write in such a way that the result is f k. See, when you write T I j n j, the result is T I, the way we wrote T I j n j. Of course, the j is being summed, T I j n j, that small t tensor T I j n j, the second index j is summed. So, in the product j will not be there, only I will be there. So, if you want to write k, yes, T k, no, but see, that should not be remain there at all. T k, if you write T k and then what is the second index? If you take I, then in the epsilon I j k there is I. So, that I should not you because then that will again mean a sum. So, you should not take I, but you see that second index will be the same as the index of n, and since it is a dummy index you can write anything, does not matter, we can write L, okay, write L. So, this term we will be writing epsilon I j k r j, and to make that force T k L n L into delta A. Okay. And of course, this has to be integrated over the bounding surface. Okay. So, since it is integrated over a surface, we will always denote by an integration with notation like this. Similarly, an integration with over a volume will also denote by an integration with integration subscript v, not by triple integration or double integration. We will usually not write double integration or triple integration, they will be denoted by just single integral sign with this notation a v. Okay. So, this is the moment due to the surface forces. Now, before we proceed further, just think about it. The other moments that will be coming is due to volume forces, okay, and the inertia, angular momentum, rate of change of angular momentum, which will be that moment of inertia into angular acceleration I into alpha. Now, this moment of inertia and this volume force both are function of volume, they depend on the volume of the element, and those integration then will also be, in that case also you have to integrate, and those integration will be integration over volume, the moment due to the body forces and the moment inertial moment they are integration over volume, but this is integration over area. Since they will be written in the same equation, it is necessary that all should represent similar type of term, that is, if those two are integration over volume, this also must be integration over volume. Alternately, those two volume integration can be expressed in terms of surface integration, but it is convenient to express this surface integral over volume integral. So, we now want to express this as a volume integration. You have done that already, you have changed integration. So, what it is? Say just think about a very simple, you have a this is a vector, okay. Here the integrand is a vector. So, integration of a vector over it over a surface is represented by how it is transformed to a volume integral, divergence. Okay. So, we will convert this to a volume integral using the divergence. How much? Yes, sorry. Epsilon I j k of course will not be differentiated, sorry, epsilon I j k will not be differentiated, it is just a constant plus or minus 1 or 0. Sorry, not x r. Okay. Now, here you see that this integral has two terms. We do not have to evaluate this integral. Now, look to this integral has two terms. The first term is simply integrated over dv, but the second term again contain a derivative. So, in terms of proportionality with delta v, what will be the result of the first and second term? Yes, the first term will be proportional to delta v or of the order of delta v, we will call it, while the second term will be order of area. Another length r j. So, what is it? Of the order of v to the power 4 by 3, So, the first term is of the order of v, the second or delta v, the second term is of the order of delta v to the power 4 by 3. Okay. Delta v, which is the volume of that element that you have chosen. Because the second term has another length multiplied, this has cube of length, this has 1, so fourth power of length. What about the moment due to the body force and the moment of inertia into angular acceleration term, or we will call inertial moment, say. What about them? Moment due to body force, in that case force itself contains a delta v, rho f delta v, you multiply that with r cross that f. So, that again have length to fourth power of length, okay, or delta v to the power 4 by 3. This is the mathematical notation by which order of is written. This means order of delta v to the power 4 by 3. So, in this moment equilibrium equation, we have 4 terms, 3 of them are proportional to fourth power of characteristic length, while one is third power of characteristic length. One is of the order of delta v, the others are of the order of delta v to the power 4 by 3. Now, again imagine that we are making this element smaller and smaller, but in such a way that the point about which we took the moment, that point O, always remain within that volume, whatever small we make it. So, when it approaches to 0, still that point O is within that volume, that is the restriction, we are never taking it outside. Now, as we make smaller and smaller, these 3 terms which are proportional to delta v to the power 4 by 3 is becoming or approaching 0 much faster compared to the other term, fourth term. The fourth term is much larger than these, when delta x is very small, the fourth term is much larger compared to this other 3 term, or that first term is much larger than the other 3 terms, but the net effect is 0, and again that is possible if that first term itself is 0, because other 3 being much smaller than it can never be able to balance it within that small scale, small length or small volume. So, that gives that the first term is 0. So, equilibrium suggests what we had T k j or T j k, T k j for a constant for a continuous function, if the t no how can we at this stage it is not TKL, TKJ. What did I write? No, I also wrote no TKL, but after this there is a differentiation. No, see, this difference is because of the result of drj drl. You can check what that different derivative will be, drj dxl, thinking of r1, r2, r3 and rl also r1, r2, r3. So, the derivative will be non-zero when j and l are same, otherwise not, and in that way that l will become j. That is this derivative drj drl. The way we have got this first term is simply by differentiating rj with respect to rl, and rj and rl, rj when differentiated with respect to rl is 1 only when j and l are same. For j and l different, this becomes 0. So, they vanish. Okay. So, only TKJ part only remains. N NL, how can NL be there? NL is not possible. Oh, achha, that normal, the normal with the derivative. Rj this NL with RL, only that L part will only the when L is same as J, only then it remains, and for that this TKL then becomes TKJ. The end result is TKJ. You for little practice or understanding, you write the terms explicitly. Okay? Taking, and if you do it for once or twice, see, these things will become I mean, you will become more confident with this notation. Now, let us come to this integration, then that epsilon I j k t k j, this integration of this is 0, that is what this term is 0, that is what we obtain from the equilibrium. Now, look to this particular integration now. This integration can be 0, but this function which is being integrated or the integrand is continuous, and for a continuous integrand the result can be 0 for all possible choice of v. This choice of v is arbitrary. The volume, that elemental volume that we choose, that is arbitrary. We can choose any volume. For any arbitrary chosen volume, this result will be true only if this integrand itself is 0. So, it may become 0 for some particular choice of v, even if it is non-zero itself, but because of some particular choice of the elemental volume, sometime it may become 0. But in general, for all possible choice of the elemental volume, if this is 0, that is possible only if the integrand itself is 0. Okay. Since choice of and what does it mean? Can you say epsilon I j k t k j equal to 0? Just think about I equal to 1, that case. Only I equal to 1, then j and k can be either 2 or 3. So, if j is 2, k is 3, then it becomes epsilon 1 2 3, that is plus 1 t 3 2, and when you make j 3 k 2, this epsilon I j k become minus 1. So, t 3 2 minus t 2 3 equal to 0. For I equal to 1, we get this equation. For I equal to 1, this results, we get T 3 2 minus T 2 3 equal to 0, or T 2 3 equal to T 3 2, or whatever way you write. Okay. Similarly, for any choice, or in one way, this T k j equal epsilon I j k T k j equal to 0 means T k j equal to T j k. Okay. You can try this with I equal to 2 or 3, that way. Practice it for a few days. Okay. Unless you will not feel confident with these notations, unless you practice for some cases. So, do that practice, and you will see that there is nothing very terrifying or nothing very special about this notation. It is only convenient and simple. Anyway, so what does it mean? T k j equal to T j k, that is the stress tensor is symmetric. The stress tensor is symmetric. You know, this is what the way symmetric matrix are written. When the matrix is symmetric, A I j equal to A j I. So, this is the transpose is same as the original. The matrix is same as its transpose. So, stress tensor is symmetric. So, what we have found based on our discussion today, we have seen that the nature of surface forces, that surface forces are basically stress, and also that this stress is symmetric tensor. And now we will see certain properties of, I think, some tensor, some matrix you might be familiar with. Or you know what are, say, tensor invariant? In terms of moment of inertia, you have, that is also another tensor you are familiar with. Didn't you come across something called invariant? This you are familiar with, that if we rotate the axis system, then the elements are changed. Each element will change. Okay, we will discuss this in the next class.